Dr. Smith for a while now. As you can see, his talk is related to aerodynamic forces and modeling. It's outside of my area of expertise, at least, so I'm looking forward to learning something new. With that, you can take it away.
Hi, everyone. I'm Melam Master. My advisor is Dr. Marilyn Smith, and today I'm presenting on the prediction of forces and moments of canonical shapes. Okay, so when it comes to the aerodynamic analysis of agile UAVs, unmanned aerial vehicles, there's a little exploration of rotor effects and quasi-steady thrust, but when it comes to the fuselage aerodynamics, there's kind of a gap. And when they do analyze the fuselage aerodynamics, the current practice is to simplify it as a point mass or do the frontal equivalent flat plate drag equation, which is basically just simplifying it as a flat plate. Both of these methods are incredibly inaccurate, and so that is why our simulation aims to solve that problem. So for our simulation, it's closer to the actual vehicle response than the prior models I talked about, the flat plate and the point mass. And it allows for the design of your UAV to be a little closer when it comes to control laws and stability characteristics to what the real life model is. As for the solution, it is in real or near real time compared to CFD, which obviously is not in real time, takes a lot longer, and is more computationally costly. And the simulation produces aerodynamic forces and moments for a wide range of vehicle configurations. You can change the vehicle configuration, whatever input you have to our simulation, and it outputs the aerodynamic forces and moments in real time. That video on the left that played, I can play it again. The video on the left is from a drone racing league simulation. Our simulation is being used by, or will be used in the future by NASA, the Navy, the Drone Racing League, and other companies in industry. Okay, so this is the overview of the simulation. It starts with the inputs being the flight conditions, the configuration of the vehicle, and the orientation of the vehicle. And then some shedding analysis done and quasi-steady aerodynamics is done. And the output of that is unsteady aerodynamics is done on that. For the quasi-steady aerodynamics, it's done through CFD, experiments, and Compass. Compass is what I've been working on the past few semesters, and I'll talk more about that the rest of the presentation. So after all of this is done, force and moment coefficients for the overall aircraft, given the flight conditions, are output. So Compass is the Complex Aerodynamic Shape Simulator. The process we follow is we take the vehicle geometry and we deconstruct the complex shape into canonical shapes. For example, prisms, cylinders, spheres, spheroids, and flat plates, among other shapes. And then we perform orientation sweeps. So we rotate the geometry of the vehicle for different angles of attack and different angles of side sweep. And at each orientation angle, we perform calculations for the coefficient of pressure distribution so that we can integrate those values to get moment and forces of each face and the overall vehicle. So for example, this little prism you see on the left, that's rotating with an angle of side slip to the free stream. And the middle image is a 2D showing of that variation of angle of attack with relation to different faces, or angle of side slip with the relation to different faces. And then the image on the right, that is the UAV deconstructed into the canonical shapes. This one is just rectangular prisms. But as you can see, it turns the complex shape into a much simpler shape to analyze aerodynamically. Compass is 5 orders of magnitude less computationally costly than CFD. So we get pretty similar results to CFD without the time and cost that comes with CFD, as well as the time and cost that comes with experimental analysis like wind tunnel tests and whatnot. So Compass is really worth it when it comes to doing the analysis and not using time and money to get solutions. So these are some of the results. So as you can see, the drag coefficient for a range of angle of yaw. The dashed line is for the flat plate equivalency I talked about earlier. And the red line is CFD analysis, and the black line is compass. So compass is significantly closer to the CFD analysis for both the drag coefficient and the side coefficient for a range of angle of yaws. It might seem like the compass and the CFD values are still different because they're not like exactly on top of each other in the plots. But when it comes to actual performance, so this is a split S maneuver. So the results of the simulations are used to calculate the position of the UAV when it's doing a split S maneuver, which is where it does a little 180-degree turn. That loop is a 180-degree turn, so it ends up 180 degrees from where it started. So the blue line is the position from the flat plate results, whereas the red and black are from CFD and compass respectively. And as you can see, the actual performance of the UAV is very similar for the CFD and compass analysis. Whereas when you do the flat plate equivalency, it's actually really different. So when it comes to real life performance of the UAV using these simulations, the compass results are pretty similar to actual real life performance. So here's a little overview of the process that everything goes through. So the user inputs flight conditions, free stream conditions, and an input file that is the geometry of the vehicle broken down into each of its faces, their positions, their orientations. And then the program takes those and it builds the geometry and outputs a plot of the actual geometry so the user can kind of see if their input file was correct and it looks like it does in real life. And then from that build vehicle, one of the things we've been working on recently is shadowing. So for example, if the free stream flight conditions are blocked to one face because there's another face in the way, that's considered shadowing. And recently we've added that because the flight conditions are different for one face if there's another face blocking it from the free stream. And so we're now considering that in the simulation. So we determine if each face is shadowed. And then we go to the flow characterization, whether it's steady, unsteady, any turbulence, etc. And then we compute the coefficient of pressure distribution for each face of the whole body. And then we integrate that coefficient of pressure distribution for each face for the whole body to calculate forces and moments of the entire body. Now we do this calculation for each angle. So we iterate over a range of angle of attacks and angle of side slips so we can find the different force and moment coefficients as it relates to the angle of attack or angle of side slip. Then after that, it goes into the rest of the analysis to do unsteady analysis and whatnot, and then the final force and moment plots are output for each of the sweeps. So one of the main things I worked on was the addition of the spheroid shape. So the image on the left, those are the geometry builds of the UAV when it was just with rectangular prisms. But a lot of drones and helicopters and whatnot, their fuselages are more similar to a spheroid shape. For example, the one on the right, you can see that's the spheroid shaped fuselage. So we wanted to include the spheroid shape in our analysis so that we could have a little more realistic analysis for some of these different fuselage shapes. So the process for this was we read in existing CFD and experimental data for a spheroid shape, so CFD analysis and wind tunnel data with that spheroid shape. We arranged it, plotted the values, and I got coefficients for data fits. For example, we got the minimum coefficient of pressure location, the maximum coefficient of pressure location, stagnation pressure locations for each of the different orientation angles. And then we're able to plot it so that we can predict what it would be for different angles that weren't analyzed in the CFD and experimental data. From that, we created an empirical formula so that you could calculate the coefficient of pressure. And then these line fit coefficients were input into the actual compass routine so that the coefficient of pressure distribution could be calculated for each face on a spheroid, just like all other shapes we have in compass. So here's one of the results we got from that spheroid analysis. On the left is the normals for each of the panels of the spheroid shape. So we need the normals in order to calculate the sign of the coefficient of pressure and which direction the force or moment are pointing in. On the right, you see the coefficient of lift versus an angle of attack and the coefficient of pitching moment versus an angle of attack. As you can see, there's a discontinuity at negative 90 and 90 degrees. We initially thought this was due to an error with the arc tangent or an arc sine or arc cosine being undefined or infinity at certain values. But when we fixed the solution, we still had the discontinuity. So that's being looked into. But one of the things we think is the problem is that the research and CFD data we have is not complete across all angles of attack. We only have it for a few angles of attack. And so our line fit coefficients aren't realistic because we're getting non-physical results in our data. And so one of the things we're working on is we're augmenting our input data with CFD analysis that we're doing ourselves. So you can see Wheeler and Wetzel are different models that we've used. And the Burke results are the CFD analysis we've done so far. We've only done it on a few angles of attack. But using these results, we can generate more accurate line fit coefficients to have better output results for the coefficient of lift and coefficient of pitching moment versus angle of attack versus side slip for the spheroid shape. Now, another thing I've worked on the past few semesters is a flat plate analysis. So the flat plate is can be a simplification of drone or helicopter rotors or different parts of the body of the aircraft. And what I did was I derived the equation from the flow over a cylinder. So this is the Glauert-Fourier series with the CUDA condition. So that's the coefficient of pressure distribution over a flat plate. When you integrate that and you get the total coefficient of lift, it's 2 pi alpha, which we know from finite or infinite flat plate theory that is the coefficient of lift of a wing. Then when you calculate the coefficient of pitching moment, you get negative pi over 2 alpha. And when you plug that into the equation for the coefficient of pitching moment for the quarter chord, and you plug in the coefficient of lift into that equation, you get 0 because flat plate theory, the coefficient of pitching moment about the quarter chord is 0. Now, one of the things we wanted to work on was doing finite aspect ratio corrections because flat plate theory assumes that the flat plate is an infinite span, and this is inaccurate because flat plates in real life are not infinitely long. So one of the corrections we did was for that finite aspect ratio, but we did that correction on the actual lift and drag values instead of on the coefficient of pressure values. And that's one of the things we're working on in the future is to change that so we do the correction on the actual coefficient of pressure values so that we can integrate it and get the lift and drag values and moment values just straight from the integration instead of doing corrections after the integration. Thank you. I'd like to acknowledge Dr. Marilyn Smith, my advisor, and everyone in the non-linear computational aeroelasticity lab for helping me and assisting me in all of my research. I'd like to open it up to questions if there are any.
I have a few just because I'm curious.
Sure.
These may be silly questions. So is there like a range of applicability for this kind of work in terms of like free stream velocity, or does it work for like decibel flows or supersonic flows?
So right now, all the analysis I've done is with incompressible,
Okay.
but further analysis is being done with the rest of the simulation for incompressible and other types of flows.
Okay. And is the idea to build up like a database that you can like put different shapes?
Yeah, so we're working on integrating many other shapes so that the simulation can be run for a wide range of shapes so that whatever geometry you have, you can simplify it as different shapes.
Okay, so you can like combine shapes and pretty cool.
So I'm not super versed in CFD, so I was curious, like, what is the major simplification that differentiates CFD from this process in terms of like that computational efficiency where it's 5 times better?
Right. So CFD analysis actually takes a mesh of the object and it runs the analyses on that mesh instead of doing just a simple coefficient of pressure distribution and integrating the values. So what we're doing is we're simplifying the actual shape into these simple shapes, whereas the actual shape of a UAV or whatnot is a lot more complex. It's not just made of rectangular prisms and whatnot. And so because of this simplification, we're able to do these analyses a lot quicker in real time, as opposed to actually getting the mesh and doing analysis on a much more complex body.
Essentially just like a mediary point between simplifying it all the way to a flat plate versus CFD.
Right. Which is why it's more accurate than the flat plate equivalency, but it takes a lot less time and cost than CFD analysis.
Maybe for a complex enough shape that may flip for the CFD is cheaper than the standard method?
Not for any of the shapes that we've done yet or are planning to do. I'm sure there could be some very complex shapes that would be more complex than CFD analysis.
Okay.
Has there been any like research done onto like how simple you can get the shape of like a walk-up or whatever, so that like you're trading off efficiency versus accuracy? Has there been like any sort of research on that?
I personally haven't looked into that, but as we know, like you can go too far on one end, like the flat plate equivalency, and you can go too far on the other end, like the CFD analysis. So we have been trying to find like a good in-between point. Okay, thank you.
Good afternoon, everyone. Nice to see a crowded room. I'll be presenting this afternoon on thermoacoustic instabilities in combustor rigs. So just to provide a little bit of background on what thermoacoustic instabilities actually are. In your combustor rig, you have your combustor where you take your fuel and your oxidizer and you burn them. And the products are the gas byproducts in addition to heat. And as a result of the emission of those gases, you get pressure and also heat, as I mentioned. And both these can be modeled as waves, as you see in the figure on the right. So with that wave, the amplitude of that wave could be thought of as the pressure magnitude or the heat flux magnitude. And as with all waves, these waves can be additive, which is constructive interference, or destructive interference if they are non-additive. And with modern combustor rigs, the geometries are too complex to be able to simplify it to a rectangle as I did in this image. So that, and in addition to the high frequency oscillations that we see for both pressure and temperature, that'll produce some, it makes it difficult to predict how these waves will, where this constructive interference will occur and how it will move as a function of time. So, and as a result of these additive waves, we can see spikes in the pressure and temperature at certain regions in the combustor, which can cause catastrophic failure. As you see in this image here, this was from JPL, where this is the injector plate. So here's where the fuel is injected into the combustor, and they allowed it to be subjected to these thermoacoustic instabilities and the temperature. There was a spike near the injectors, as you can see, that caused the system to fail and resulted in the image on the right. So when it comes to combustion instabilities, for specifically in a canannular rig, which is shown in the image on the right, there's two primary modes of oscillations as they propagate through the combustor. The first is longitudinal, or standing waves. So that is shown here, where if you imagine these as pressure waves or the amplitude of the pressure or where the pressure peaks, this is where the products are emitted from. These waves will propagate down the combustor, be reflected off the end and come back. And as I mentioned, because of the complex geometry, it can be difficult to say where these waves will be at a function of time. And we see where areas here where there are a lot of high pressure amplitudes at one point, we'll see a pressure spike, which is what I mentioned previously will cause the combustor to fail. So that's longitudinal, but for the purpose of this project, we focus mainly on azimuthal or spinning waves, or the spinning mode of oscillations, which can be broken down into clockwise and counterclockwise. And that's a little more difficult to show in terms of standing pressure waves, but that's what we focus on in this project. So in order to be able to model these instabilities, we first have to model the combustion. We can treat the flame response as a control system with two outputs, the heat and pressure. And with all control systems, we can use a block diagram to model it, as you see in this image. That's in the time domain. If we take it and put it in the frequency domain, we can produce this state space model, which shows the heat and pressure as functions of the eigenmodes of the thermoacoustic instabilities. And you can take that state space model and break it down into a PDE, which is our governing PDE for the response and the thermoacoustic instabilities. Here, eta represents the eigenmodes of the thermoacoustic instability, so that's the second time derivative. Omega naught in the second term represents the frequency of these instabilities. And then it shows that it's a function of the eigenmodes and the first time derivative plus z, which is a noise term, which I'll get to at the end. So with that model now known, we can begin to model our instabilities. So for this, we started with a MATLAB tool called solve-SD conditional averaging. It input the combustion parameters to a certain level of fidelity, which included the net growth rate of the instability modes, the saturation constant, which is typically just kept at 1, the frequency of the oscillation, as I mentioned previously, and the standard deviation of the noise term, and it would output the functional form of the amplitude and the amplitudes themselves. Now, it would calculate this using this expression here. The derivation is really long, really gross, and didn't really fit into this presentation, so I just provided this, this function. And in addition, in this tool, there was some additional processes done to filter data, sorting it into bins, etc. And with that, we could take the outputs of this tool, the amplitude and the functional form, and input it into another tool in Python called regression singleton. So it would take those two inputs and it would plot the functional form of the instabilities versus the amplitude, and it would output the coefficient for the least squares regression, which we also made in this Python tool. And these coefficients could be directly related back to the combustion parameters, which we set previously. So this function relies on a method of curve fitting, and we spent a lot of time trying to figure out what the best method to do this was. We ultimately settled on a single function least squares regression tool from SciPy, a SciPy optimized curve fit. With this tool, we could set the functional form of the regression, and it would input the amplitude and the functional form of the amplitudes, and it would output the coefficient, which I mentioned could relate back to the combustion parameters. So after running for our first iteration, we had this set of these inputs, which are nominal. They're reasonable for an experimental setup, and we outputted this plot and those combustion parameters. As you can see, the expected parameters are also the inputs, and we achieved parameters that didn't quite match what we expected. And this can be explained as you see this region of the plot. We have our regression line in blue is a really good fit for our data. The data was plotted directly. But at lower amplitudes, we see that there is a much higher variance. And we believe this was the result of, at these amplitudes, we are not noticing a dominant mode of oscillation. So as I mentioned previously, we had the clockwise and counterclockwise. These instabilities occur when one mode becomes much more dominant than another. And at these amplitudes, we see that there was no dominant mode, so we didn't want to include that in our model. So as a result, when we restricted our domain further from, in the previous iteration, it was 0.2 to 1.5, now it's 0.8 to 1.3. So it was just that domain of well-fitting data. Our plot obviously looks a lot better, but we see that our coefficients or our combustion parameters still don't match our expected results. This was a bit of a surprise when we first saw this. We believe that what we found, which I explain here, as we see, there's still a pretty significant % error between the achieved and expected combustion parameters. And what we believe we found is another set of combustion parameters that produces an identical functional form for the given range of amplitudes, which we understand is a result of the fact that we're using a regression technique which is non-deterministic. And in addition, the model was not up to, it was a certain level of fidelity, but it wasn't full complexity that you would expect. And this difference most likely comes from our noise term, which I will again get to in just a minute. So with the noise term, we modeled it as white Gaussian noise, which has a standard normal distribution of equal power. You can see on the top right figure, that's our normal standard distribution, and the bottom right is the equal power at all frequencies. The purpose of the noise term is to help model the combustion noise, or small uncertainties that you can't really account for explicitly. So it's almost like a fudge factor because it is independent of everything else in the system. It's added at the end of our governing PDE. But the actual combustion noise isn't quite as simple as white Gaussian noise. It's actually much more complex. So we try to increase our fidelity by changing our white Gaussian noise to colored Gaussian noise, which is still a normal standard distribution, but it's no longer equal power at all frequencies. So it's still the standard bell curve, but the figure at the bottom right would no longer be a straight line. It would also look like a bell curve. But what we found with this colored Gaussian noise is that obviously it added a lot of complexity in terms of the computing power required, because now you add an additional term into where the peak of that bell curve would be. But we didn't really see significant improvements to our results. So for the purpose of keeping this code efficient, we left it at white Gaussian noise for now. So in terms of future steps with this project, as I mentioned previously, we're still unable to distinguish between multiple sets of combustion parameters that produce the same functional form. And as I said, it's because it's a non-deterministic process based on curve fitting and stochastic averaging. In order to filter out these identical, or these sets of combustion parameters that produce this identical functional form, our current best guess and most simple guess is to provide an initial guess for what one of these or multiple of these parameters might be. That way we can base where we're looking off of that initial guess. We can also try to increase the fidelity of the noise term, but that's a very difficult process and could be a project in and of itself. And what we believe would work best in order to produce the expected results is to use a multifunction optimization technique as opposed to single function. We expect the multiple functions to be able to filter out some of these parameters sets that are not what we expected based on our set frame. And as I mentioned with the noise, despite being independent of system parameters, it's still a very significant term. It has a very large amplitude. And we only really tested a single type, but there's a lot of work that goes into noise that we have yet to consider. With that, I'd like to thank everyone at the Combustion Lab who was involved in this project, and I'd like to open it up to questions. Cool.
I'm going to ask some questions.
Sure.
So I don't fully understand what a combustion parameter is. Are they like thermodynamic properties or?
So that was an area of the research project that was done before I joined the project. Yeah. So those values can be described as functions of parameters that are set, such as the fuel injection rate, not really the geometry, the injection temperature, and controllable system parameters. So the first, I guess, phase of the project was to create a model that takes those experimental conditions and solves for the combustion parameters that I described.
And so that the white noise was a simple, so it's like a computationally tractable but unrealistic model of combustion noise. The colored noise was like too computationally expensive but more realistic.
It should be, but the results, it didn't create a very large difference in our results, right, despite being computationally more advanced. So it should, realistically, the noise shouldn't really be Gaussian. Right. So that introduces a whole new level of complexity, but colored keeps it as Gaussian, which is easier to model for our purposes, but it didn't really fix anything.
we know what kind of shape we expect that noise to be? Is still
not yet. I think one of the graduate students in the lab is actually working on that project.
And how long did this model take to run? So when you say it becomes too complicated,
with white Gaussian noise, it was actually pretty fast. It only takes a couple minutes because it's two different programs. You have to do the tracking of the file directories. But all in all, I think about 10 to 15 minutes per simulation, which isn't bad.
Yeah. And that's what the white Gaussian is?
Yes.
And how long was it?
I don't remember.
Okay. Yeah, that's fine. Right. Okay. So our last speaker for today is Adhiraj. He's going to present on something that sounds pretty cool to me, laser diagnostic methods in combustion. So go ahead.
Hey, good afternoon. I'm Adhiraj, and as you said, I'm presenting on laser diagnostic methods for turbulent premixed combustion in a swirl stabilized combustor. A little background breaking down that long title. What's turbulent combustion? Turbulent combustion, as the name suggests, is combustion in a turbulent flow. And it has been found through experimental and computational research that there's a difference in the combustion process between a turbulent flow and a non-turbulent incompressible flow. So some of the effects of turbulence on combustion that have been studied experimentally and computationally are that there's enhanced mixing of the chemical species as well as the temperature within the reactants. Anyone who's taken an aerodynamics class might have heard of turbulent mixing. That obviously helps accelerate the reaction rates, and it affects the flame speeds as well. However, there's limited research, especially limited experimental research, on how combustion affects turbulence. And that's something we've tried to explore through this project. Turbulent combustion is relevant because jet engines, stationary gas turbine engines, and internal combustion engines all mostly use turbulent combustion. So by studying these effects, we really understand the systems around us a lot better. So the combustors we used in this experiment are swirl stabilized combustors. And the reason we chose these sort of combustors are because they represent the flame in a gas turbine engine really well. They're stable flames and they're small in size. So the stability in a swirl stabilized combustor, as you can see in this diagram here, is caused by the recirculation zones. There is a little V-shaped flame, that's the blue V in the image here. And as the products leave and the flame the reactants leave the combustor, the flame forms products, and these products tend to be hotter and lower in density than the reactants. So that leads to a higher static pressure because there's lower centrifugal force, and that essentially causes a downwards pressure gradient where it's pushing the flame downwards and helping it stabilize. And there's two recirculation zones. There's the outer recirculation zone and the central recirculation zone. That's the ORZ and CRZ labeled in this diagram. And the flames we study here are premixed flames. That's the fuel and the oxidizer are mixed together before they cross the dump plane. So what are the objectives of this experiment? First, as I mentioned before, we want to study how combustion affects turbulence. More specifically, we want to see how the turbulence production is affected by different flame controlling parameters such as the equivalence ratio or the Reynolds number of the flow. And finally, we want to study and try to recognize what conditions this turbulence production is actually significant. And we can do this by measuring the 3D velocity field of the reactants, flame, and the products, and also get a planar distribution of CH2O, which is formaldehyde. So the diagnostic methods that we chose for this experiment are tomographic particle image velocimetry, or TPIV, and formaldehyde PLIF. So using TomoPIV, we hope to get a three-dimensional, three-component velocity field. That's what the 3D and 3C stand for. And the advantage of PIV is that it's independent of chemical composition, and that means we can use the same method to get the velocity field in the reactants, the flame, and the products. And then formaldehyde PLIF will help us identify the flame location through the planar distribution of formaldehyde. Both these measurement methods can be used simultaneously, and so we can get both the velocity field and the planar distribution of formaldehyde at the same instant. And it's just an image of some data we got, but I'll talk more about that later. So what is particle image velocimetry? What I mentioned in the previous slide, TOMO-PIV is a type of particle image velocimetry. So I just want to give a little background about this laser diagnostic method and why we chose it. So particle image velocimetry is a flow visualization method. And the way it works is we first seed the flow with small particles that are usually on the order of microns. And this helps us visualize the flow. We then take images of the flow at a time t, and then a time t plus delta t. This delta t is calibrated really precisely, usually on the order of microseconds again. And from these two images, we can calculate the displacement vectors of the particles, and we know our delta t, so that helps us generate the velocity field. We also use lasers to actually illuminate the seed particles and illuminate the flow so that we can actually see it clearly in these images. So we usually have a dual head or double pulse laser so that we can get the first pulse when we want to take our first image at time t, and then second pulse at t plus delta t. And using a double pulse laser helps us ensure that we have a good enough intensity for both images to get good enough data. When you use one camera, as usually done in PIV, you can get a two-dimensional velocity field of just a planar field of view. You have a laser sheet, and you have a domain within that sheet, and that's what you're imaging. And you can separate the in-plane components of the velocities. But if you want to go a little further than that, and you want a three-component velocity field, you can use what's called stereoscopic PIV, in which you have two cameras that have slightly different perspectives, so they're at an angle, and they image every particle a little differently because they're obviously viewing from a different angle. So this helps us resolve the third component, which is the in or out of plane component of the particles being imaged. And this diagram can help us understand both 2D PIV, which I mentioned in the previous slide, and 3D PIV. So the camera above the laser sheet is the single camera that can give you a two-dimensional two-component velocity field, and the one below is the two cameras together will give you a two-dimensional but three-component velocity field. Now we can take that a step further, and that's where we get to tomographic PIV, where if you use three or more cameras, you can now get a three-dimensional velocity field with all three components of velocity. So now instead of using a laser sheet, we're actually using what you can imagine as almost a rectangular slab. It's considerably thicker, and the thickness is a lot more. And all four cameras will simultaneously take measurements of the same region, and they're usually placed with two on one side of the laser sheet and two on the other side of the laser sheet. Using the images that these cameras capture, you can generate 3D intensity fields, and then there's some really complex 3D correlation algorithms that help us reconstruct the volume that we were imaging. This is an underdetermined problem, and that means that a given set of images can represent a large number of volumes that are imaged, and there's some really interesting math that goes behind it and trying to identify which one the actual image represents, but I won't get too much into the details of that. And the reconstruction technique used is called multiplicative algebraic reconstruction technique. This is a computationally expensive technique and takes a lot of time to run. There have been some advances, and there are some faster methods that are still based on MART, but MART is very reliable, so it's still commonly used. So why did we pick PIV, TOMO-PIV? Before I get into that, this is a little image of just one data set, or one data point from one camera out of four that shows the two images between at time t and then t plus delta t, and that's what our seed particles look like, and that's what's used to generate our velocity field. So why at TOMO-PIV? Because first, it gives us the instantaneous velocity measurements, and we can measure the velocity at multiple locations at the same time. So using this image here, you can figure out the velocity at all these different points within this field of view. Whereas if you were using a method like a hot wire or LDV, you would have to move your probe and you'd only be able to take a measurement at a certain point at a given time. It's non-invasive, so you aren't sticking any sort of probe into the fluid that could affect the behavior of the fluid. You can visualize the flow, which is always helpful. It's more intuitive. You can verify the quality of your readings. And as I mentioned before, compared to stereo PIV or regular PIV, now you can measure the velocity component along an entire slab. So there's considerable thickness there. And this is a really accurate method. There's high spatial and temporal accuracy. There's obviously some limitations and disadvantages that come with most methods. So precise calibration is required. The image you saw in this previous slide, the height is about 50 millimeters and the width is about 25 millimeters. So when you're aligning your lasers and your cameras, you do that by hand. The small errors can cause large errors in your process data. Sometimes your particles will cluster, and then there's large particle clusters that cause scattering. They might also not be in focus, as you can see with these really large particles, which look like they have halos around them. These are on these data points that could cause errors in your data. There's particle number density requirements. So you want to make sure that your flow has an acceptable particle number density at all parts of the flow. Again, going back to this previous image, you can see that there's the products are a lot less dense than your reactants, which there's like the inclined line, that's your reactants, and then the central part is your products. So the number density of the particles also changes as the density of your flow changes. You want to make sure that you have an acceptable density in all parts of your flow. The seed particles absorb energy. So we say this is non-invasive, but there's obviously some impact of putting seed into that flow when compared to no seed at all. It's computationally expensive. So if you want to measure one data point using ThermoPIV, that's 8 images. If you have 1,000 data points, that's 8,000 images for just one test case. We try to run, I think, about 50 cases. So 400,000 images, each of them being 5 megabytes. You can imagine what sort of data we're talking about. And it's an expensive setup. Laser is expensive. These are high-speed cameras. You need some very precise optics. So it's not easy to acquire this. Moving on to the next laser diagnostic method we use is PLIF, or planar laser-induced fluorescence. And this is what we use to capture an image of our flame. So the way PLIF works is that we pulse a laser at our flame, and there's certain species that get excited because they absorb the energy from the laser. And there's certain frequencies that excite them the most. And for formaldehyde specifically, it's 355 nanometers. Once these species get excited, they then emit light at certain frequencies, as you can see from the frequency spectrum here. There's peaks at certain frequencies, and between 370 and 40 nanometers, that's what's been plotted here, and that's what formaldehyde emits. The fluorescence is then captured by a camera through an intensifier, and that helps us visualize the flame. The species that we select for PLIF are usually intermediates in the combustion process. So they're only present where the flame is and not in the products or the reactants. And hence we only get signals from where the flame is, and that can help us capture both the position and the shape of the flame. This is an image that we captured while running our experiment. And as you can see, that's a pretty turbulent flame. So why PLIF? PLIF obviously helps us achieve our objective and determine the flame shape as well as the position at the same time. It's got great temporal and spatial accuracy. It's again non-invasive. PLIF doesn't, ThermoPIV needs seed particles. PLIF doesn't even need that, so it's even better. And it has a planar field of view as we want, and it can easily be combined with PIV. So we could take measurements using both methods at the same time. There are limitations with this as well. First being it requires an intensifier. So if you can imagine the species that are now fluorescing and emitting light, they're going to do that in all directions, and your camera is just pointed in one direction, and so it's not going to get a lot of signal from these species. So you need an intensifier to actually make this signal measurable and usable. The problem with that, the intensifier doesn't know what's signal and what's noise. It's going to intensify everything. There's going to be some scattering from seed particles in the configuration we used because PLIF does not need seed particles, but we also combined it with ThermoPIV. So as you can see in this image, you'll see a few very bright spots there, and that is scattering from seed particles of the laser light. There could be some interference from other species. So as you could see in the frequency spectrum, there are certain peaks, but there's still emissions at other frequencies. So there are other species that could also emit light at those frequencies. There's problems with the signal to noise ratio. As you can see in this image, the noise is pretty high, so if things aren't calibrated well, your data might be pretty bad. And again, it's an expensive setup. You need lasers, you need a high-speed camera, the intensifier is expensive. So yep, that's always a problem. So going into the specific setup of this experiment, as mentioned before, we use a swirl stabilized combustor. We had a methane air flame, that is a premixed flame, a radial swirler with a conical block body, and we varied certain flow parameters. So we changed the equivalence ratio, and we measured 3 points between lean and stoichiometric combustion, and then we also varied the jet velocity. We had 3 different combustors that we would switch out between test cases, and our first combustor had the swirl number of 0.55, the other 0.75, and the last one with 1. For this experiment, we defined swirl number as the ratio of the momentum flux between the azimuthal component and the axial component. This is an image of our combined experimental setup. So the green laser and the green path is our ThermoPIV laser lens path, and the 4 cameras at angles around it are the cameras that are capturing our ThermoPIV data. The purple path is that of our PLIF laser, and the blue box is our intensifier with the attached camera that captures our PLIF data. These are just some specifics of the instruments we use. So we use a 532 nanometer laser for ThermoPIV. We have our 4 cameras with a bandpass filter so that we'd only get light measurements that were actually from the laser and not other sources of light. We had the region we were imaging was about 50 by 25 millimeters with about 3 to 5 millimeter thickness. We used aluminum oxide seed particles, and as I mentioned, they're really small, 0.3 micrometers. And yeah, we used LaVision Davis to reconstruct our velocity fields. For PLIF setup, we used another Mindiak laser, this time of 355 nanometers, so it could excite formaldehyde. We had an intensified camera, as I mentioned before, a camera on lens, and then our filter again was a bandpass filter to ensure that we'd only get fluorescence from our formaldehyde species. And finally, for general operation, we measured ThermoPIV for reacting and non-reacting cases, compared the data from both. PLIF obviously would only be for the reacting case because you want to visualize the flame. We measured at 3 swirl numbers, 4 to 5 jet velocities between 0 and 30, and 3 equivalence ratios. The PLIF pulses were placed temporally between the ThermoPIV pulses, so we would take the first ThermoPIV image, then the PLIF image, and then the second ThermoPIV image. And this ensured that we would get data at the same instant and comparable data. And the PLIF plane of measurement was the center plane of the ThermoPIV volume. We have, again, MATLAB scripts and Davis scripts processing this data simultaneously. And these are just a few images of some data we acquired. So you've seen the first image with just one camera capturing one instant. The one in the middle is the velocity reconstruction that Davis spit out for us using that first image. And the third one's actually streamlines for non-reacting case, which help us visualize some of the recirculation and the turbulence. And obviously there were some more challenges once everything came together. There's an even larger amount of data. Between different test cases, we would have to change our delta T and C density settings because you'd have different swirl numbers, different jet velocities. At higher jet velocities, we'd also face problems with flame blow-off. And there were some internal camera trigger errors. Small errors in terms of timing could also lead to unusable data. And finally, there was noise from seed particles, as I mentioned before, and there was scattering from the combustor when the laser would hit the actual combustor. But in the end, with proper calibration, we were able to rectify most of these issues, and we do have a good usable set of data. So I'd like to thank, obviously, all of the combustion lab, Dr. Steinberg, and Askar for letting me work on this project, and I'll open up to any questions.
Great. Again, sorry, I just have two questions because I'm curious. So, do you know how many particles that you need to the combustor with? Like, is it like 1,000, a million, a billion?
So the way we would do it is because the thermo PIV, when it's processing the data, it splits the field of view into what we call voxels, like pixels, but now since we're talking about volume, it's voxels. And we would set requirements to allow for a certain number of particles within a certain voxel volume that we were planning to process with. For example, I believe we were around about 10 particles per voxel.
Sure.
That obviously varied with the size of the voxel that you're processing with. But so we'd run like a preliminary case, and we ran all the data through Davis to ensure that we were able to recreate the velocity field properly, and then we varied the particle density to ensure that we were getting reliable data.
Right.
But if your particle density is too low, it won't really work with PIV. And then there's other methods like I think it's PTV, particle tracking velocimetry, which actually follows so that's like Lagrangian method, which follows the particle through the fluid. And then if it's too high, you have laser speckle velocimetry. So for PIV, yeah, there's certain requirements, and we use the preliminary cases to identify them.
Okay. And you were using aluminum oxide as your seed particle.
Right. Yes.
Chemical, I guess. But does that have a risk of actually like combusting at high temperatures, or does that only like absorb energy, or does it have a potential for releasing energy? You know, some particles better than others to use?
There is obviously a lot that goes into picking the seed particle. I don't fully remember the details of it. Aluminum oxide does not. Based on the conditions we were running at, would not really react or combust.
Okay.
But there's obviously some potential for other reactions. Yeah.
Stop bothering. Okay.
Oh.
Okay.
You have, like, after writing all these, like, there are like one person asked to like how combustion does affect turbulence.
So we're still in the process of processing our data because we've taken help from Georgia Tech's PACE supercomputers because we were running one case in 5 days, and with 50 cases, that's like over a year of processing data, and then you have post-processing. But I'm not an expert on turbulence or combustion, but based on the proposal and what was explained to me, don't quote me on this, the way what we're trying to understand is so turbulent formations or eddies are formed at a variety of scales. There's a large number of scales. So you have like large scale eddies, and then you have like really small scale ones as well. And in turbulence, the turbulent kinetic energy is formed at these larger scales through shear, and then through advection, it's passed down to these smaller scales where it's dissipated as heat. The flame scale is one of the smaller scales. So when you have combustion, there's a peak in there's production of turbulence at a smaller scale. So now there's potential for this energy to move back towards the larger scale, so transfer from smaller to larger scales. And we're trying to identify whether this is significant and at what parameters this is significant.
All right.
Thank you.